Alright, so in this video, I'm going to be talking through pages 15, 16, and 17 in the notes packet. This is all about asymptotes. And so asymptotes occur whenever a function kind of gets infinitely closer to a line, right? It'll get continuously closer to that line without ever hitting it. And you can have both horizontal and vertical asymptotes. So this is kind of the example that I drew to make that clear for you guys. So what is drawn there is this function here. And so we have a horizontal asymptote at y equals 2, and we have vertical asymptotes at x equals 1, or x equals -3, and x equals 1. And so the question is, you might be asking is, well, if we see a function, how do we know what its asymptotes are? And so one thing you can do is you can always just plug it into your graphic calculator and visually locate the asymptote. So here you can eyeball and see that there's your horizontal asymptote, and here are your vertical asymptotes. But you also can derive them from the equation. So for the vertical asymptotes, they're going to occur anywhere where the denominator of any part of the function is 0. So for example, if I see this function here, I know that the vertical asymptotes are going to be at x equals -2, x equals 0, and x equals 3, because those are the three values that are going to make some part of this function have a 0 denominator. And so that's where we're going to have a vertical asymptote. So the vertical asymptotes come from whenever the denominator is equal to 0 in any part of the equation. The horizontal asymptotes, the analytical approach is a little bit more complicated here, so it has to do with the power on the top and the bottom. So, for example, with this equation here, the top has a power of 3, it's a cubic function. The denominator has the power 2, it's a square function. And so whenever the numerator is bigger than the denominator, you're not going to have a horizontal asymptote. The reason for this is because the top is getting bigger at a faster rate than the bottom. So as x gets really big or x gets really small, we're not going to trend towards any certain value. We're going to go off to infinity or -infinity. But if the numerators are the same, that's what you see here, right? ax squared plus b over cx squared plus d. Both of them have a square power. And in that case, because the powers match, your horizontal asymptote is the ratio of the coefficients, in this case, a over c. So this one up here is actually an example of that. If you see, because we have two x's on the top, if we were to kind of multiply here, the top would be 2x squared plus 4x, and the denominator would be x squared plus 2x minus 3. And so here, because we have x squared there and there, the horizontal asymptote is the ratio of these two coefficients, in this case 2 over 1, or 2. The third case that can happen is if the bottom has a bigger power than the top, and in that case, the bottom is going to get much bigger at a faster rate than the top, and so as x gets arbitrarily large, this is going to become bigger than this, and so their ratio is going to trend towards 0. So if the denominator is smaller, you're going to trend towards 0. That being said, with these types of questions, if you are ever stuck, so you can use this analytical approach if you're able to remember it. If not, always plug into your graphing calculator and you can visually identify the asymptotes that way. This is especially true because you want to be very careful when using the analytical approach. For example, if we use the analytical approach right over here, we were talking about where the vertical asymptotes are where the denominator is 0. Well, if you look over here, you would say, oh, well, that should occur at x equals -1 and x equals 2. Right? Those should be our vertical asymptotes based on that analytical approach because those are the values that make the denominator 0. Yet if we look at the graph of this function, we see the asymptote at x equals 2. Right, that's right there. But there isn't another one at x equals -1. And you might be asking, why is that the case? And it's because if we look closely at the function, we have x plus 1 on the top and x plus 1 on the bottom. And so those two actually cancel each other out. So this function could be written 2 times x minus 2. So it's kind of a phantom x plus 1 there because it cancels out. So you just want to make sure that if you're using the analytical approach, you're simplifying as far as you can first. All right, so on these two down here, all we're doing is sketching our asymptotes. So we can see visually that's going to be right here. It's going to be down here. And then we write that x equals -3 for the vertical one and y equals 2 for the horizontal one. And then over here, we draw them in again. And then we get x is equal to -1 and x is equal to -3 for the vertical asymptotes. We get y is equal to -1 for the horizontal asymptotes. Okay, so for these ones down here, I'm asking you to sketch a function of all of them by plugging that into your graphing calculator, which I can do over here. If we go 1 over x, we graph it, we see that it looks like this. And that means it's going to look something like this. And we can put the asymptote in there. And the vertical asymptote is going to happen when x equals 0. We can confirm that with the analytical approach, right? This is going to be, the denominator here is going to be 0 when x is 0. And the horizontal asymptote here is going to be y equals 0, which we can see visually. And we can confirm using the analytical approach from the last one, where it's the ratio, or sorry, because the power in the denominator is bigger, it's automatically 0. Right, now if we look at this one, we have 2x plus 3 divided by 3x minus 4 graph. It looks like this. And so that you can kind of sketch that to say that it goes something like this, and then something like this. So we see that we have a vertical and a horizontal asymptote here. But their exact values is less clear than it was on the first one, because they're not at 0, right? In fact, they're not at an even number. So this is where the analytical approach is helpful, in that we want to look for the vertical asymptotes. We want to see where is the denominator 0. In other words, when is 3x minus 4 equal to 0, which we can solve by adding 4 on each side, dividing by 3, and we see that this vertical asymptote is that x is equal to 4 over 3. And then for the horizontal asymptote, well, we see that the powers are the same between the top and the bottom, right? We have an x to the first and an x to the first, meaning that the horizontal asymptote is going to be the ratio of that coefficient on that lead term. In this case, it's going to be y is equal to 2 over 3. Okay. Let's go to the last one. Let's graph this, and so we have x divided by x squared minus 1. And if we graph that, we see that it looks something like something like this. So visually, we see that we have vertical asymptotes at 1 and -1, and a horizontal asymptote at y equals 0. We can confirm that using the analytical approach as well. So what are the values that make x squared minus 1 equal to 0? Well, that's when x squared is equal to 1, which occurs if x is 1 or if x is -1. And again, with the analytical approach, the power on the bottom is greater than the power on the top. And so that means it's automatically 0, right? This denominator is going to get bigger at a much faster rate. So as x gets arbitrarily large, it's going to trend towards 0.